Hi, I'm Ian Mercer. Welcome to my talk about the semantic web. You could be forgiven for thinking that the semantic web was really complicated. There's a lot of information out there, there's a lot of terms, and it sounds really complicated. But I'm here today to tell you that it's actually really simple. You don't need to know all of this stuff. Put that away. What you need to know, the only thing you need to know at its core, is the semantic web is triples. No, triples. Triples are the atom of data. A triple is a subject, a predicate, and an object. So an entity, some kind of relationship to another entity maybe. Subject, entity in your typical system, person, place, thing, account, whatever. Predicate. The predicate is typically a verb or a verb plus a preposition. So, Ian has name Ian, has age, has friend, relationship, whatever. And then the object. And the object is either a constant or another object. So for a property, we're really talking about a constant, and for a relationship, it's another object. It's another entity in the system. So for example, the kitchen has a name kitchen. So this is a property of the kitchen. The kitchen is contained in the first floor. So this is an example of a relationship specified as a triple. There's a sensor on the wall in the kitchen, and it has a type of sensor, a motion sensor. So here we're expressing a type relationship, but again, it's just another triple. Here we're saying the motion sensor is a subclass of sensor. So now we're doing statements about the classes. We're sort of 2 levels up in our reasoning about what's going on in our system. But again, it's just another triple. Triples are the atom of data. There is no simpler approach. We can't do pairs. We can't do Mary has, John has dog. We don't know if Mary has the dog or John has the dog, or they both have a dog, or they both have the same dog. It doesn't work. We need the triple. You've seen how we can express both properties and relationships using triples. We can do structured or unstructured data. Structured data is just a very boring set of triples repeating for every property of an object. We can do data or metadata, and it's complete. The triple is complete. We can represent any other form of data using it. We don't need anything else. Let's compare that to a SQL database or a relational database. We might have a table called person, and it's got somebody called Fred in it. In semantic web, we can represent that by saying that, Fred is a person, Fred has a name, Fred has an age, Fred has a weight. But we're not limited. You can have 2 names if he wants in semantic web. We also give Fred a name, an ID, a URI, Fred, and a namespace. In this case, I've just put X. Typically, it would be a proper URI. But then we can also put other relationships in there. We can talk about the table itself. We can talk about the columns in the table, what attributes of the columns and what units they have. And so the whole data set can be self-describing. I can give you one file that tells you all about the people, but also tells you how to interpret the data about the people. Whereas a SQL table doesn't give you that. You don't know that the age column is an age column other than its name, typically. But RDF is verbose. Every single property gets listed out as a triple. Let's compare that to a graph database. In a graph database, we might have a document at each node. And so we can put all the properties into that document. And then we have a relationship between them, like contained in an edge. So very similar to semantic web, looks pretty comparable. And it's certainly faster for properties. It's a great way to represent your properties because they're all together. We can load them all in one go. But we can't tell you anything much about that contains in. It's just an edge. It's just a label on an edge. It's not a node itself. In semantic web, we put a node in the middle. And that allows us to go meta, all the way up to reason about what that relationship means. For example, in semantic web, we can say that the is open to relationship is a subclass of being adjacent. So if one room is open to another, then it's also adjacent to another because it's a subclass of. The graph model didn't allow us to express that. When we serialize semantic web data, and you could be forgiven for thinking that serialization was all about semantic web because everything is RDF, XML, blah, blah, blah. But it's not. It's a triple. RDF XML is one way to serialize it. There's another way, Turtle. There's several ways, but Turtle is a good one. I like it because it's more readable, it's more concise, it's easier to write. Key concept here is that nodes have a URI, like I mentioned earlier. If it's the same concept in two different ontologies, two different linked data sets, then it has the same URI. Here's an example of some Turtle first triple language from my home automation. So we start off with a subject. I've got a concept called a tank in my home automation. It's a noun and it's the first use of the word tank. And its prefix is HA, it's my home automation prefix namespace. We can create a bunch of relationships or predicates referring to that tank, and we can say that it has some labels, it's got a glossary entry, it's got a type, and it's got a part meronym of, come to that. The first three are all constants, and so it's got two names and it's got a glossary entry. The next two are other entities. So here we're saying that the tank in my system is of type tank noun 2 in WordNet, because in WordNet they have two tank concepts, or maybe more. And the first one is, a track vehicle that fires projectiles, and the next one is a hot water tank in a building. And that's the one I want to key into, because I want to merge my ontology with WordNet and be able to let people write questions about the home automation system using words that I've defined as well as defined in WordNet. And then the last one, part meronym of. Now, if I was writing an ontology, I would have just gone, hey, the tank is part of the heating system, is part of, would have been my predicate. But there's an existing predicate in WordNet that was created by people with a much better understanding of words and meanings than you or I will ever have. And this is properly called a meronym. Meronym. It's like an enemy. Meronym of another word or another meaning. And so we use an existing meaning, an existing ontological entity when it's been defined for us. We don't create new ones. We've also got kind of a split going on here. There's assertions that we make about instances. We've got all of the equivalent to the SQL table. We've got all of the instances of buildings, rooms in a building, and what class they are. And then we've got assertions about the classes themselves. So this is sort of an upper level where we're saying that, hey, a room is part of a building. And it's, all rooms are part of a building, as opposed to here where we're talking about a specific instance like the kitchen. Taking another comparison, in Azure, they have a digital twin, and they have a concept there called a model and a twin. They're both graphs. One is reasoning at this higher level, one is reasoning at the instance level. Very similar concept. Now this is important. We already mentioned how Freddy could have two names. Well, in semantic web, we have a thing called the open world assumption, which says, if I haven't made a statement, it could be true or false. Anybody can come along later and define the truthiness or falseness of some other statement. This means that you can add assertions to any existing ontology. I can take the WordNet ontology and I can build a whole ontology on top of it. I can combine two ontologies from different companies and link them together to create, my new ontology, referencing them both without having to redefine or copy any concepts that are in those other ontologies. So when you're building your ontology, you should go out and look at all the existing ontologies. Don't reinvent the wheel. We don't need another ontology for units of measure. We don't need another ontology for geographic names. They're out there. Go use them. Don't create new URIs for the same concept. If there's one over here, use it. And don't try and version nodes with the same meaning. The meaning should be constant over time. If you get the meaning wrong up front, it means you messed up front. That's the very rare case where you would ever add a new version. You can add a whole new version of your ontology, but you would use the same URIs for every concept that exists in the old ontology and then add your new ones on. You wouldn't change the version numbers on things that already exist, that are already linked, because with linked data, other people may have already linked to your model. There's lots of great ontologies out there. I mentioned a couple. I mean, you should go look at OWL and WordNet and Friend of a Friend, and you can go look at the Wine ontology. That's a good sample ontology for understanding some of the concepts. OWL, I've touched on OWL briefly. I'm not going to go into it in detail today. OWL is an ontology that lets you define your own ontology much more precisely. With our open world assumption, we could add anything we like to any of the ontologies we've shown so far. But with OWL, we can come in and say cardinality. We can say that person can only have one name. It's not true, but we could say that in OWL. We can also express enum types with mutual exclusivity. We can say, no, you can only be one of these three values in this property. There's many levels of complexity of OWL, and you need to use a reasoner for any of them, and it gets complicated very fast. The semantic web also has its own query language called Sparkle, which is a brilliantly simple language, brilliantly powerful, but very quickly any query becomes reasoning and potentially becomes slow. There's different levels of reasoning. Simple entailment is one I kind of recommend that everybody should know about. It means we can just follow transitive relationships. So if this room is in this floor, and this floor is in this building, and this room is in this building, we've reasoned that the room is in the building just by following the same link through the graph. Beyond that, everything else becomes hard and slow. As soon as we start reasoning about the predicates themselves, it becomes much harder. You have to visit the same node multiple times with different assumptions in order to come to the result. Unlike finding a path through a graph, like route planning, how do I get from A to B, I only ever need to visit each node once to get from A to B. Once I've found the optimum path, I'm done. But with a complicated system where you can reason about the edges as well, and the state of the system as you consider that edge is complex, it can take forever. But you can also save all that back to the graph, having reasoned it. So you might run reasoning ahead of time and then save the results. Simple entailment, already mentioned. I won't go into that in more detail, but that's the most useful one. And yeah, when the predicate is a node, all bets are off. Reasoning becomes very hard. Touch on one more thing before I close, which is a lot of people want to put things into trees. It's natural. Everybody loves trees. The world loves trees because most things in the real world can only be in one place. The book in the library has to be on a shelf, in a section, in a library. Ignoring symlinks, the file on disk has to be in a folder, in a folder, in a folder on a disk. Filing cabinets, same. All charts, we put people into trees because we can't handle graphs. Yahoo tried to put the world, the web, into a categorization system. It failed. The world is not categories. And biologists, of course, they go to extreme levels. You get the tree frog and it's got like 20 levels above it in the hierarchy. But, the real world isn't shaped like that. The real world is best modeled as a graph because you hit things like, well, I want to create a taxonomy for animals. Well, is it a mammal or a bird? Great. Node, tree. Can it fly? Oh, that's easy. Does it lay eggs? That's easy. Does it have a beak? That's easy. Oh, hang on a minute. Penguins. Bats? Duckbill platypus? Now we're really screwed because we can't represent them in a taxonomy that has all of those in as split points in the tree. So don't use a tree when it's really a graph. It will ultimately lead to problems. You will get to situations you can't represent. You'll get into arguments about, well, is it more a flying thing or more an egg thing? which is more important to me? And we see that in geopolitics too. You know, do we divide the world by religion, by race, by country? And you know, that's how wars start. So don't get into wars. Start with the basis that it's a graph and you can't go wrong. And some people go, well, we'll just use tags. Tags are easy. We don't need, you know, we don't need taxonomies. We don't need categories. Let's just tag everything. We can be top 40 and we can be country if we want to. We can put tags on building pieces. And, hey, it's a sensor and it's a temperature sensor and it's an air temperature sensor. This creates lots of new problems. Tags are just a string. They're ambiguous. They don't convey a semantic meaning like a relationship in a graph. You can get around that a bit by putting namespaces on. But really, tags are equivalent to, you know, is isomorphic to, labeling the nodes on a graph. It's duplicative. We end up with the same label in lots of places. It's hard to maintain and it's non-semantic. A category, meanwhile, is isomorphic to a tree, which is a degenerate graph. If you've got a graph, you can represent categories. If you've got a graph, you can represent tags. The same is not the other way around. They do not have the same expressive power. So, in conclusion, if you're trying to represent knowledge, use a graph. The more semantic web-like you can make it, the better, because it's complete. You can do everything in the semantic web. But maybe you don't want to. It's not always efficient to store all your properties in a semantic web way. My favorite way of representing data when I'm building a prototype is to have a document database, so I can have documents with all my entities in, and they can have any properties on that I want, and I can query properties very quickly. But all of the relationships between those entities, I model as semantic web triples. And what that means is that the middle relationship is also a node. It's an entity back in the document list of entities. And with that structure, it's very flexible, can pretty much do everything. Thank you for listening. I've been working with graphs for many years. My smart home is based on graphs. My natural language engine is based on semantic web principles. I have a graph library on GitHub that you're free to go try and use, and it starts with a semantic web-like approach to graphs. And I work for Willow, and where we're building ultra-scale IoT, massive skyscrapers and rail networks, tens of thousands of sensors, and they're all based on a graph. Graphs are fantastic. Start with a graph. You can't go wrong. Thank you for listening.